Today we're talking about section 2.3. The learning targets are up there at the top. We're talking about where a function is continuous and then the intermediate value theorem in this particular section. So when we talk about a function being continuous, like the basic definition that you've known for the last few years is, can I draw the entire thing without picking up my pencil? So today we're going to kind of talk about what is the actual definition and how can we verify it and prove it using mathematics. So the first part we're going to talk about is continuity at a point. So an interior point is a point inside the function somewhere, not one of the endpoints. And so it says a function is continuous at an interior point C if the limit as x approaches c of that function is f of c. And we've already talked about this a couple of times here in class. We've said, all right, if we can get the limits from the left and right to equal each other, that means the limit existed. So then now does that limit equal the function at that point? So if you refer back to your 2-1 notes, we did this graph in section 2.1, and that's where we kind of talked about it. So you may want to flip back and check some of those notes that we talked about there. But then we kind of left it open-ended when we talked about the endpoints. And so here it says the function is continuous at the left endpoint, or it is continuous at a right endpoint if the one-sided limit equals the function value. So remember, we don't have to approach from both sides if it's an endpoint, simply because the function doesn't exist on the other sides. So if a function's not continuous at a point, then the word we use is discontinuous, or we call it a point of discontinuity. So for example 1, it says find the points of continuity and the points of discontinuity of the greatest integer function. So we're talking about the ceiling function, and this should say the rounding down function, so that was a typo. So we're talking about that int x function. So I know we talked about this in our graphing packets. So we have close dot, open dot, and we can continue this on. And so I'm just going to draw a few of those. You could continue it on if you wanted to. But so we have to investigate, where is this continuous and where is it discontinuous? So I think the easier question is to answer where it's discontinuous. So where is this function not continuous? So this function is not continuous. It's discontinuous at all integer values. Which means that this function then is continuous when x is not equal to an integer. So you can notice it's continuous everywhere else, but we pick up our pencil and move on. So we're going to see 4 different types of discontinuities in this section. When we look at these 4 different types of discontinuities, we've seen all of these before except for probably this last one. But the first one is called a removable discontinuity. So a removable discontinuity results in a hole in the graph. And when you guys did some of these graph type questions in pre-calculus, we talked about a function, and I'll just put it in factored form to be nice. So if I gave you this function, f of x equals x plus 2 over x or times x minus 3 over x plus 2. When I can actually remove the factor from the problem, then this one we would say there is a hole at x equals negative 2, so that particular factor. So when we draw the graph of that function, it will end up looking like this, except at negative 2, there's going to be a hole in the graph. A jump discontinuity is one just like what we've got up here. I'm not going to draw it again. You may draw it again in your notes, but this one is full of jump discontinuities. And it's any time you've got this jump from one part of a function to another part of a function. So it's where the function has a breaking point and then continues on. So typically you see this in a step function or in a piecewise. The infinite discontinuity is one where we talk about the vertical asymptotes. So you've seen a few of these already this year as well. So a vertical asymptote, again, I'm going to give you an example of x plus 2, x plus 3, all over x plus 1. So nothing cancels out. We can't remove anything. So this one would have a vertical asymptote at x equals -1. You can also think of some more basic functions like 1 over x. This one has a vertical asymptote at x equals 0. And so that function looks like this. So we've seen quite a few of those functions already. The last one is an oscillating discontinuity, and that's for a function like y equals sine of 1 over x. And so on your graphing calculators, you should graph that function so that you can see what that looks like. Obviously, we're going to have an issue when we plug in 0 for x. It's not going to work. We can't divide by 0. And so just a very crude drawing of that is it starts off like this, and then it gets really quick, and then it kind of slows down as we move away. Again, I would want to graph that on the calculator just to get a good picture of what that looks like. Make sure you're in radian mode. But it becomes a mess right here at x equals 0 because this thing starts oscillating really quickly. So when we talk about these continuous functions, this definition here says a function is continuous if and only if it is continuous at every point on that given interval or domain. It doesn't have to be continuous on every interval. So we could say 1 over x is continuous, just not at 0. But for x is greater than 0 and for x is less than 0, we could call it a continuous function. So we would just say there's a point of discontinuity at x equals 0. So a couple of properties that are in here. I'm not going to spend a lot of time on these, but if I have two functions, f and g, and they're both continuous, then I'm allowed to add and subtract those two functions, which we do all the time. Think like x squared plus x or x squared minus x. Those are both continuous functions. We add and subtract them all the time. We can multiply them, f times g. We can multiply them times constants. So I could say k times f or k times g. So that's an example like 2x squared. I'm allowed to just put a constant out front. And then the last one is I'm allowed to divide two continuous functions, f divided by g. The only caveat here is we have to provide the fact that g cannot equal 0. So last but not least is this idea of composite functions. And it says if f is continuous at c, so we have a continuous function, and g is continuous at f of c. Notice it doesn't say at c, it says at f of c. Then the composite g of f of x is continuous at c. All right, so I want you to look at this function. We have a function inside of another function. So what function is inside and what function is on the outside? The function on the inside, I'll warn you, is a pretty big function. There's a lot of stuff in it. And then the outside function is nice and basic. So I'm going to have this pause a second to ask you that question. So what I'm noticing is this inside function, and just because it's written this way, g of f of x, I'm going to call this inside function f of x, which is x times sine of x over x squared plus 2. And all of that function is stuck inside of the absolute value function. I'm going to put that way over here. So g of x is absolute value of f of x. So they're asking us to show that this is a continuous function. So according to our definition up here, x times sine of x. X is continuous, sine is continuous. So according to this definition, I'm allowed to multiply those. So I'm just going to put product of two continuous functions. And then down here, I have the sum of two continuous functions. X squared is continuous and 2 is continuous. So this one is the sum of two continuous functions. And then all together, I have the quotient of two continuous functions. And the one thing I had to keep in mind is that the bottom can never equal 0. Well, I can never square something and get a -2. So I'm never going to get a 0 down here on the bottom. So here I have the quotient of two continuous functions. So this f is continuous. And they said if f is continuous, then I can put it inside of absolute value. Now, absolute value is also a continuous function. So our composite definition says if I can take a continuous and put it into another continuous, then we can say G is continuous. All right, our last definition, and this one's a big one. It's an important one, and we're going to have other definition sheets that we'll put this on. But the intermediate value theorem for continuous functions. So it says the function y equals f of x is continuous on a closed interval. So we're going to be talking about this in class a little bit more, but this is one of the conditions that's necessary for the intermediate value theorem. It's on a closed interval. And it will take on every value between f of a and f of b. And it says draw a picture to illustrate. So I've already done this. I'm going to just kind of pull it up here. And you can feel free to pause the video if you need to. But what it's saying is we've got from a to b. Here's f of a and here's f of b. It hits every single y value from f of a to f of b. And you can see it actually goes below that and it actually goes above that. But all that the intermediate value theorem guarantees us is everything in between these two values because it's a continuous function. So a non-example here, I put a piecewise function. 2x minus 2 goes from 1 to 2. And then the function 3 from 2 to 4. Notice there's this jump discontinuity. So this one we can say is not continuous, and the intermediate value theorem would not work because it's not a continuous function. Every y value is not hit here. I don't have the values between 2 and 3. So if you need to, go ahead and pause the video so you can get that picture down. Otherwise, you're golden.